Thanks very much for coming to Breaking the 16K Barrier. This is a technical deep dive on multi-machine rendering, determinism, and the future of where we're planning on taking this. So just a couple of ground rules. There's a bit of assumed knowledge as you come into this particular topic. You understand what notch builder is. You understand what a notch block is. You understand what notch standalones are. You've used exposed properties before, probably with a media server. And you've probably worked in multi-machine setups, not necessarily with notch, but you might have worked with maybe multiple media servers all plugged together. So with that knowledge, you're equipped to roll through this. So I've got to be honest, I lied. This isn't just about the 16K barrier, but if I told you what it was really about, I'm not entirely sure you would come. Yeah, this is about a lot more than just the 16K barrier. But we'll start with the 16K barrier that a lot of us have hit in the past. And this 16K barrier exists because GPUs can have a texture size of only 16K by 16K. So whenever you render into a texture, you are limited by this texture limit. There are other limitations depending upon your system setup as well, but the majority of the time it's this limit that is stopping you from being able to use a single GPU to do 20, 30K wide canvases. So, if we've seen one thing with keynotes over the last couple of years, it's they take their screen and they make it wider and wider and wider to the point where it doesn't even fit on here. This is Citrix's keynote, and honestly, the screen goes like another third on either side there. And it definitely breaks the 16K barrier. You know, it's not necessarily a huge amount of pixels necessarily because it's a ribbon, but we are well and truly past 16K. And usually you're going to have to do something like this. You'll put certain screens on machine 1, and you put other machines other screens on machine 2, and you have to make sure all those machines are synced together with gen lock and frame lock. And people are using Notch in these setups already, but they're doing it with some constraints. They're ensuring that content doesn't go across machines. So, and we'll talk about that in a second. People are using baked 3D animation to be able to baked model animation so they can run those across multiple machines. And Ryan's got a talk on this tomorrow that's definitely well worthwhile going to, where he talks a lot about baking. People are using keyframed animation, so you just have the same keyframes running on each of those machines doing the same things. Notch, for the most part, our cloning animations work happily across different machines. They're fairly deterministic. And most of our procedural animations are as well. But the time it all goes wrong is when you do this. That particle system that needs to roll across all those machines. And it's a simulation. And particles need to know where they are in relation. The particles need to know where they are as they hand off between the different machines. It's just not possible at the moment. And this applies in lots of different areas. It's not just particles. You've got rigid body physics and fluid and gases and things like that. And so for fields within Notch, you have this issue too. You're also really challenged when it comes to interactivity, because if you have, let's say, a Kinect camera, which can only connect to one machine, what do you do with that if that is affecting a whole bunch of particles and that needs to be distributed across different machines? So we're not just talking about pixel limits, as I mentioned before with 16K. There are other applications which are hitting limits as well. So with the advent of augmented reality, you are now having to render your real-time notch scene from multiple different angles. So you might have 5 broadcast cameras in the studio, and you need to be able to render from all of those perspectives. But not only the different perspectives, you're often rendering different plates. So you'll be rendering a composite plate, which is going over the feed at the front, and you might have LED on the back. So you have to render both those plates. And if at the moment you're having to render both those plates on the same machine, which obviously creates some overhead limits in terms of what's being able to be achieved fidelity-wise. We just generally hit the performance limits of a single CPU quite regularly as well. I mean, that's just the nature of life. And any time a new GPU comes out, everyone's just maxing it out in the first 30 days anyway. That's one of the ways this has been dealt with in the areas of like IT is they've gone away and stopped producing these mammoth big Xeon machines, and they're starting to divide up the workload into these little blades and into smaller units of computing. And I can't say this for certain, but I can imagine a place in 5 or 10 years' time where we're starting to see smaller units of machines being used on these on productions and projects, maybe looking after one head of output. Who knows? That may happen, but we need to be ready for that. So, what are the patterns we see at the moment when people are trying to do these big shows? Well, one of the things we see at the moment is a lot of pre-rendering of video, if you can do it. So that big particle effect, they won't run it real time. They'll just render it out in Notch. We get all sorts of great feedback on this. This was a designer from LA a couple of months ago. He said, "It's funny, we've been going back and forth." And he wanted to, I think he was trying to use a fluid simulation. And we turned it on and we said, "Hey, it's going to be a bit slow, just so you know." And he turned around and said, "It's funny you call this render slow. It took about 5 minutes to output. This would have taken at least 9 hours to render from Cinema 4D on a dual Xeon and comping in AE. I could kiss you guys," which I prefer he didn't. "Thank you for giving my life back. I have more time to be creative and be with my kids." So Notch is already solving problems in these really large canvas spaces. It just so happens that we're doing it in an offline manner. So other types of workarounds, I've mentioned some of these before, baking animations, and then playing those back on the different machines. Downscaling happens more often than we would like to admit. And we often don't tell our clients that $500,000 they just spent on that LED is actually being run at half res, but it does happen. And then the last thing that you've been able to do with Notch is to run certain types of effects deterministically. So I appreciate that we have lots of different language speakers in the room, so I'm just going to qualify what determinism is. So determinism is the ability to take a common set of input variables, and then output the same result each time. So the classic case of this is about random. If I can seed my random, then every time I run that random through, I'll get the same output at the other end. And we've actually had this ability to be able to run particle systems deterministically. At the bottom of the screen down there, you'll see a checkbox, which is in the particle root node, which says deterministic. And when you do that, as long as all the inputs are the same, you will get the same particle output on each of those machines. That's been fine and dandy, but there are some issues with it. Those inputs that we need are really, really specific. You need perfect inputs for every frame. And that often involves gen-locking all those machines together, having absolutely perfect time code and frame lock. And you need completely stable frame rate to be able to achieve this. Because in a simulation, let's say a fluid simulation, if the delta time between a frame is different from machine to machine, then you can throw that simulation out. And that difference in the first frame turns into a much bigger difference in 20 frames, 30 frames, 40 frames, moving on. It's also really slow for a bunch of reasons I'm not going to delve into, but you have to order all the particles and have them mathematically processed in a certain ordered rate. And that's actually really slow and not very efficient on the GPU. And then there are occasions on various different GPUs where you can get small arithmetic errors, especially if you do certain types of instructions out of order. And those very small errors, as I've said, you get this butterfly effect, a tiny error here in 10 seconds. It's like an entirely different fluid simulation on your screen. So determinism, despite our best efforts, is not getting us to the place we need to be for multi-machine rendering. So, what do we need to do to try and solve some of these challenges? Well, we know that we need to be able to divide and propagate the workload across multiple GPUs and machines. And to be able to divide up the workload, we need to be able to do two things. We need to be able to distribute the render state across the instances. And when I say render state, that means the whole encompassing of all of your simulations, your fluid simulations, rigid body, physics simulations, all the inputs, they need to be all the outputs need to be distributed across all the render instances. And secondly, if you're going to start delinking these pieces of work and put them on different GPUs and PCs, you need to be able to, in a fairly pragmatic way, remotely control those instances from a single machine. So this is it's a slightly abstracted environment, but in most setups, you have a control machine. That's probably your machine which is, in a show environment, is sequencing your show, or it may be taking various types of control inputs. And then we have all of these GPUs lined up, and we're just going to call those GPU instances for the moment. Those instances could be separate PCs, or they could be multiple GPUs within a single PC, and we're not going to make any distinctions between those for the purpose of this talk. So as I mentioned, we need to be able to distribute various states, particles, fields, rigid body physics, but also we need to be able to distribute captured geometry. So if you're connecting from a LiDAR scanner and you have a mesh that exists on one PC, you need to be able to push that out to all the other PCs in a quick manner too. Right, so the risk with this talk, when we set out to do NotchCon, everyone said, don't do any really complicated demos on stage, because that would be a really, really bad idea. And then when I came to this talk, and it was like, well, unless I actually show people this working, no one's going to actually believe us. So please bear with me. This is you can see here I have multiple PCs set up to be able to demonstrate it. I'm sure something will go wrong as I go through, but I want to demonstrate some of these techniques to you. All right, so for the purposes of this demo, here we have a very simple particle system. This is just one of the template samples that you get in Notch. This is a development build that has some of these new distribution features in it. What we can do now with the particle root node is we have a set of networking settings at the bottom. And by turning on network distribution and turning on master, I can broadcast to the network the particle simulation that is taking place on this machine. And I'll talk through some of the details of that later, but it's UDP, so you can just put the 255 on the end and you can start broadcasting out to the network without too much issue. So I can sequence, change all of my emitters, change anything else that I want. Very normally, it doesn't impact on any of the other aspects of Notch. It's just taking this, taking the output of the particle simulation and pushing it down the pipe. Now, once I've created my particle simulation here, I can export this to a standalone, and I'm going to push this standalone out onto another machine. So if you look here, this is my machine A, yeah, and these are my machine Bs, yeah. So I've got two GPUs in my machine B, two 1080 Ti's in this machine. I've got one GPU in this machine here. So you will know that we are on the second machine because you will see a nice rock face as we go and look at that machine, background on those machines. So on my second machine, I have here the standalone that I have exported from the network sender. So I'm going to fire up my standalone here. And you can see the two GPUs I have in here. SLI link is disabled, just if you're trying this at home. And I've got a display connected to each of the GPUs. So I'm just going to choose here 1920 1080. Actually, no, I'll do it a little bit smaller for a reason you'll see in a second. And I'm just going to run this on the first GPU. He says. Okay, I think I'm going to have to reboot this machine. I'm not entirely sure why this isn't working. Okay, whilst this is running, I'll tell you just a little bit about how this works. Rather than sending the particles every single frame, we send the particle simulation at a frame rate that you can set yourself. So we're going to send it at 10 frames per second. By doing this, we can reduce the bandwidth which is going through the network. And what we do for all the frames in between is where you actually interpolate. So when the particles are getting distributed, they don't just distribute their position, they also distribute their velocity as well. And then we interpolate for the in-between frames that position based upon that velocity as it arrives on the other side. And we're nearly up. You'll see a packet size setting in there as well. So different switches have different MTU settings, and you are able to actually control the packet size depending upon the switching infrastructure you have in place. Hurrah, we're running. Good old Windows. Okay, so on our master, we are distributing out this the network particle system. And then if I slide across to here, you're looking at one of the GPU heads on the second machine, right? Now, the motion is smooth. I'm doing a lot of emitting to purposefully show you that emitting only happens at 10 frames a second. But if I put those two together, you can start to see the distribution effect. Yeah? Okay. So we'll switch back to here. So that's one GPU rendering out. I'll now show you, I'll just switch across to here so you can see what I'm doing. We'll do 1280 by 720. Right. And then I'm going to run this again. I'm going to put it on the second GPU. Oopsie. Just going to put it to the right resolution. 1280 by 720. On the second GPU. All right. Okay, so that's GPU 0. That's GPU 1. GPU 0, GPU 1. Yeah? As you would hope, it's pretty seamless. Yeah? You're definitely getting the same particle system arriving at the same time on both GPUs. Yeah? And this applies to multiple PCs. It just so happens that I've got two GPUs in the same PC. Yeah? Make sense? I wanted to show you, just to show that this truly is real. I'll just put this on a slide halfway between the two. I can change any of my effectors that I want, so I could turn off the turbulence effector entirely. It's not going to move anything at that point, so let's put in a velocity effector. And attach that. And now you can, I'll just up the velocity amount, 5. Now you can start to see it blow away on both machines. Yeah? So you can make all your creative changes. There's no need to re-export this standalone on the basis for the receivers. You only need to, because the state is just getting pushed entirely at that point. Make sense? Okay. So we've just demoed there one GPU pushing its state out to 2 other GPUs running on another machine. Just a little bit about the setup. I've got a 10 gigabit Ethernet card in both of these machines. For a 64K, 64,000 particles, you're looking at about 280 megabits per second running at 10 frames a second. So there's still some headroom. I don't actually need a 10 gigabit connection in there, but we're obviously in the office testing millions of particles and seeing how far that we can push it. And I don't have those final figures on how far we can push it yet. But I've happily got it up to like 250K without too much issue. I've talked about the interpolation. So there's your 0, 10, and 20 frames and all the interpolated frames in between it. Now, a couple of considerations here. Distribution of simulation is not free. Yeah, there is a penalty to this. So the computer which is doing the simulation has to run its simulation on the GPU, download it to the CPU, and send it out over the network. Yeah, and that has a cost associated. Not only that, that process of simulating, downloading, pushing out to the network, receiving it, and then uploading takes time. Yeah, it's not much, and I've said 3 to 4 to be very pessimistic. You can get it down to just a couple of frames, but you do need to bear that in mind. Now, one of the features that we're putting in is if you're running a simulation on machine A and you're receiving on machine B, we can delay the rendering of the simulation on machine A to keep it in sync with the one on B. So you just put a bit of a delay on the first one, and the two things come into line. When we're running at 10 frames a second, obviously the interpolation looks after all the intermediate frames, but when you're emitting, you're still only emitting at 10 frames a second, and that needs to be borne in mind as well. But you can very artistically get around that without too much issue. And we've talked about network bandwidth. Once you start getting up to a couple of the simulations, you're going to want a 10 gigabit Ethernet adapter and switch. Right, so what are some of the side benefits that we get out of this process? Well, the first one is that we can do sensor result redistribution. So I mentioned before that on our machine A here, I could be running, taking a connect input, and I could push that mesh to all the other machines, or I could have particles being emitted and have that pushing out to all the machines. And this has been a real bugbear, this whole sensors space, and we start to really get around that with this type of setup. The other side of it is that for the first time, we're starting to do multi-GPU with Notch. This is the first step in that direction, but you've seen there the separation of processes out into multiple GPUs to make use of it. Right now, we're using the network layer as our distribution method between GPUs, but there are other methods that GPUs can talk to each other with. One of those is SLI, which you've seen on the NVIDIA cards. But there's also peer-to-peer DMA methods as well, and we may explore those more fully in the future. Right, so that's distribution of state. Now, the second part of this is about distribution of control. So, in this context, we've had a unit of computing, which is the simulation taking place on this machine, or it could have gone on the other machine, but we need to be able to remotely be able to control those simulations. And what we've come up with is this concept of a proxy block. And right now, you have a regular block, a regular Notch block, and you take that block and you put it into your host application, generally media server, and you hit play, and the media server says to the block, these are all the control parameters you need to go and set, render it for me, and give it back to me. Yeah. Now, all that a proxy block does is it takes away that rendering functionality, and instead of just using the inputs internally, it broadcasts them back out across the network. Yeah. So it just becomes a remote control. So it's a proxy block because obviously it's a proxy for doing real rendering. So in this context, you might have your media server running the proxy blocks, And you might have standalones running on other machines, running the simulation, the particle simulation, and pushing it out to the other machines there. Right, let me give you a quick demo of this. Hopefully this demo goes a little bit more smoothly. Okay, so what I've done here is I have taken a fairly straightforward project, and I've exposed some parameters. I've exposed the size of the boxes that are in this simulation. So these are the things that I'm going to be changing. That's what it looks like running on this machine. Now, I don't have to make any other changes. I don't have to set up any network configuration within Builder at this point. All I have to do is go away and export a different type of block. Yeah. So in the project menu, you can now click Compile Proxy Block, and you can put that into your project. I'm just going to demonstrate this with D3 today, but it works across all the other media servers straight out of the gate. There's no changes or updates that they have to make. So there's my 16K remote. Yes, I want to replace it. Click OK. Right. At the same time, I'm going to set up a standalone, create a standalone application, and I'm going to push this to my second machine. Oopsie. All right, 16K remote. We'll replace that. Yes. Okay. Right. Okay. So on my on this machine here, my second machine, machine B, I'm now going to go and run my 16K remote project. We'll do it at 720p again. All right, there's the project. It'll run and it will animate. Now let's come back to my A machine here, and let's fire up D3. And as I said, this works on all media servers straight out of the gate. We haven't required any new changes from media servers to utilize this function. Okay, D3's decided it doesn't know. There we go. Thank you, finally there. God, I've got a run of it today, don't I? All right, so when you load a proxy block into a media server, it gives you a couple of extra parameters straight out of the gate. One is the IP address of the machine you are going to talk to, and the second is the port number that you are going to be controlling on that slave application. So if I go back to my media server here, I'm just going to start my standalone, and when I start my standalone, I'm going to say proxy receiver port, and we're going with port 8005. Let's do this again. Okay. Right, now we are running. And if I now put this on a halfway, I'm going to try and be clever and change the parameters across, and sorry, I need to restart D3. You're not going to have to do this in future, but the slaves need to be running before the master, but that's going to change in the future. Right. Come on. Okay. So now when I make the changes, you can see them remotely pushing across the network to the standalone that's running. Yeah? From within the block. Okay, so now I have remote control over multiple aspects any exposed parameter that I've chosen there running across the network. Does that make sense to everybody? Yeah? Cool. So I can have multiple instances of these slaves set up and just be seamlessly controlling them. It's not, you don't just have to have one. So, there are a couple of fringe benefits to this, this method. We've obviously developed this functionality so that you can have these remote simulations running on other machines, be able to control them. But when you take remote control and you do rendering on the slave, when you put those two things together, you can get what's called outboard rendering. So this is the ability to be able to run your rendering on a separate machine and then pipe it back to your host when you want it. Does that make sense? So I'll demonstrate this to you quickly now. So let me sort these around. Here's D3 just hosting the block, just the same as we were doing before. And there's the remote render taking place. And what I did, which you didn't see, was I enabled NDI out of that standalone. And if I go into devices now, I can choose that NDI source, and I will add a video layer. And set the media to video in. And now we have a remote rendered instance of Notch passing its video back to the host. And if I make my changes, those changes are all reflected through. Yeah? So the host is not doing any work. Yeah? The slave is doing all the work. Does that make sense to anybody before I move on? Yeah? Okay, good. So why is this useful? Well, it opens up a whole set of new hosts to the Notch environment that weren't previously accessible. So if your host is a low power, doesn't have an RTX or a 1080 Ti or something like that in there, you can have this low powered host with a separate PC with a high powered GPU in it, and you can be feeding those elements back up to the low powered host. Yeah? Or you can have one host which has got a whole set of other renders taking place on other machines and pushing those back, units of rendering that they wouldn't have been able to contain within one machine. Make sense? Yep. The second part is, because a proxy block doesn't do any rendering, it doesn't have to be hooked into the Windows DirectX ecosystem. Yeah? So all of a sudden, we can start to write blocks that run on Linux and Mac OS X, and you can have a host which will not be rendering, but they're able to control from those platforms and push out to Windows renders. And there's been a long request to be able to interoperate with some of these other platforms. And by outboarding that rendering to a Windows machine and keeping your host as Linux or Mac, you get a good distance there. Perhaps this isn't used so much in live production. When you start getting to the post-effects world, there is a huge mix, especially in the Linux space, of hosts that need to be on different platforms. There are other fringe benefits. I'm just using this one as an example. So VJs tour, I don't know if there are any VJs here today, but the common VJ setup that exists right now is they don't tour with racks, they tour with laptops. And as it stands, we pretty much see any VJ setup with Notch. You'll have Resolume running on one machine, and you have Notch running on the other one, and they'll either be NDIing or capturing back to Resolume, and they'll have this crazy complex OSC setup talking between the two systems, just so they can offload the workload of Notch to another machine, because they don't want it on the Resolume machine. It's just not powerful to run it on one laptop altogether. And with Proxy Blocks, now they can seamlessly control those remote, their second machine running Notch, and it can live happily in that host application without these crazy complex OSC setups, and the NDI setup will become a little bit more simpler as well. Make sense? Cool. So again, it's not free. There's obviously a 3 to 4 frame delay after you've grabbed that render from the other machine, pushed it all the way back up to the host again. So there's lots of applications where this is not going to be appropriate. If you are working in IMAG effects in live production, you do not want to be adding 3 to 4 frames of additional delay into that setup. But if you're rendering interactive effects, maybe on the basis of black tracks or any other type of interaction, you can get away with these types of delays. Or if you're rendering high quality content, and we see this a lot in AR, high quality content on a machine where you really need the full stretch of the GPU, it works really well. There's obviously complexity. You need to know what you're doing with your network setup to be able to go away and do these things. Most of you do understand all of that. And there is a reliance on a network infrastructure. Some of the future possibilities are where we might take proxy blocks. So right now you have to manually configure the NDI return back to the proxy block, to the hosted app. Maybe we'll make that a seamless background feature so you don't have to worry about it. So the proxy block itself has a little NDI receiver in it, and it retrieves it back. Or maybe we ditch NDI altogether and we go, not Chelsea streaming. Maybe. What about if there's multiple GPUs in the same machine and you don't need to use the network layer? Well, perhaps we can use peer-to-peer DMA or things like SLI to be able to move those between the GPUs. Maybe. And the Mac OS X and Linux host application support will be something that we'll pursue. It's not happening right now, but it's something that we will start to venture into towards the end of this year. Right, so just a quick recap. We're distributing the render states across instances using network distribution, like you saw with particles today. And we're remotely controlling those instances with proxy blocks. So can we do this with these 2 solutions? Yes, we can. Absolutely. We can distribute that particle state across the machines without any issue and run across the screens there. Can we distribute the state of the particles or the fields across multiple machines, each looking after a specific point of view from a tracked camera? Yes, we can solve that problem. And this is the start of looking at breaking away from single GPU ceilings. Yeah, I'm not making any big promises or claims today that this is going to solve all those problems right now, but it is these are some of the foundations of the architecture which are needed to be able to move us in that direction. Again, the big metal versus small metal, we've just demonstrated how that works across lots of different nodes. So let me just talk a little bit about how we're releasing this, because this is definitely going to take a little bit of time. In the next release, 0.922, we're calling it Plummet Yourself Experimental Release of these features. Yeah? And at this conference, as you can imagine, there's a whole set of really advanced Notch users who will jump on this, thrash it to pieces, and really work out how this works in a production environment and in their workflows. So that's our aim with 0.922. In stage 2, we're going to add more raw functionality to things like the distributed simulation. And in stage 3, we'll start doing smart management. So we're going to reduce the number of clicks which are required to be able to go and do this. So giving machines roles, and roles, so you might have the media server might say to the block, okay, you're going to be role B. And you know that role B is going to be, okay, I'm going to do that simulation, and I'm going to do this type of render. Yeah? So it's that type of management coming through, and we'll be working with the media server partners on designs and the best way to implement that across them. So here in detail is what you're getting in 0.922. You're getting network distributed rendering for distributed particles, and also distributed geometry at low poly rates under 12,000 polys. So that should get you to the kind of the Connect real sense distribution stage there. We're putting in support for proxy blocks, so the command pipe will be in, but that return of video of either NDI or capture is going to be up to you. There's a couple of things that I have not even touched on here. One of them is tiling and window configurations. So if you have a block right now and you set up a camera and you run that block across different machines, they all have the same camera. But when you're running in a tiling situation where you need to render certain portions for different machines, that needs a whole interface and communication with the media server as to which tile along that long ribbon you're going to be rendering. And those are protocols that we're working with the media service to define at the moment. There's also neighbor pixel sensitive effects. So if you can take, for example, a blur at any given pixel is a function of all the pixels that surround it. Yeah. But if you are at the edge of the canvas, yeah, what do you do about the pixels which are rendered on the next machine? Well, there's ways to get around this. You've got things like adding in a safety boundary on the end, so your kernel size, so the blur doesn't overlap the end of that. But there's other things like glitch and other effects like that that need to be handled. The likely way we're going to handle this is we're going to probably classify our nodes in two groups: those which are distributed rendering safe and those which aren't. And the list will probably just grow as we convert nodes and say you are going to be more distributed rendering safe. And as I said, this is a journey, and I hope today we've given you a snapshot of what we're doing now and what we plan on doing over the next year. There are some really big projects in the pipeline on 2019 which are going to be using this. Fixed install architectural is really driving us to get this in quickly. Yeah, we're looking forward to seeing what happens with those projects. So, has someone got the time? I haven't got my watch on me. 10:02, okay, right. So we've probably got time for 5 minutes of questions. Does anyone have any questions?
In that example, you exported the block and you have deterministic particles, but there's also light. If you were to adjust the light, it would work across the instances as well, or no?
No, but you can do a live edit at the same time to the standalone, and that will reflect the rest of the changes through onto the slave machine.
Okay. Yeah. Kind of piggybacking on that with the idea of using multiple cameras, like in an AR scenario, you have to create, say, 5 cameras, and that needs to be in all of them, even though one machine is using lit.
Well, in the last release in 0.921, we handed control to the media servers of cameras. So you have an exposed camera. So the host application that's running it can actually dictate where the camera is. So you set up one camera, and then the host, which is usually looking after the camera tracking, is the one that's saying, right, that's where you are.
But in this case, it's not a standalone machine, so it wasn't inside the server.
Yeah, I was demonstrating it with standalone, but like the distributed state, the simulation you might run in a standalone, or you might run it in a block. You can run it in a block or a standalone, but that distributed state can be distributed to blocks as well. Doesn't just need to be distributed to a standalone. I was just using it for the ease of showing it on 2 GPUs. Any other questions? Yes, at the front.
So you said there was 3 to 4 frames of delay.
Yeah.
So if you have like a difference in the ultimate, they usually lead times are like sub 1 millisecond or sub 2 milliseconds.
Yeah.
So if the frame is 16 milliseconds, so I guess the first question is like where does extra?
Where's the die? Yeah. Yeah.
And then the second question is, actually just back to my question earlier about separating the UI from the rendered.
Yeah.
How does it handle like different frame rates? Like theoretically, if you're running your master at 120 frames per second,
Yeah.
you're guaranteed your downstream 60 frames per second instances always have frame
Yeah.
data.
Yeah. So I'm going to answer the second one first. Yeah. So you are delinked from the rendering FPS on each machine. Yeah. So in the case of the particles getting distributed, that was getting sent at 10 frames a second, which is pretty arbitrary. Yeah. I could be running this at 120 or 60 or 70 frames per second, whatever I wanted. But the data is arriving on a thread on those machines, and when it gets the opportunity to do the next present, it'll present it out onto there. The delay, as I said, I was being quite pessimistic there because I don't want to make grandiose promises. The delay is in the download that's coming from the GPU to the CPU, and then the CPU actually processing all of that and pushing it out down the line. then they're going, you're right, absolutely, the ping time's really low. But at the other end, it then has to be reassembled and then pushed back up to the GPU again. Now, I know that in the future, when you actually start tweaking up the gen lock on these things, you're probably going to be able to bring that down to a really tight number. But yeah, I'm going to leave it in a pessimistic world at the moment until we really hone this in. Scott?
Proxy on the media server, can it output as well? Or is it very much controlled?
So we might do a mixed mode, maybe. I'm looking at Matt.
Proxy block at the moment doesn't do anything but just sits down. So it's not even licensed.
Yeah.
You can have a proxy block and then a normal block.
Yeah, you absolutely can. Yeah. Yeah.
The other blocks, the standalone blocks, can't just output them as a normal, like Google full screen.
Yeah, absolutely. Yeah, the only reason I wasn't doing it full screen was so you could see the background, so they were actually on two machines, and I was not trying to pull the wool over your eyes. Matt raised an important point there. Proxy blocks do not require a license on the host machine to be able to run. Yeah, only the rendering nodes, the machines we're actually doing rendering and simulation, will require a license. Yes, at the back.
Can I get a proxy block back into Notch, like on a pre-composed layer, and so therefore push out the renderings that I only need in 2D in my main machine?
So, so if I understand you correctly, you want to be able to loop back your particle distribution. Yes, you absolutely can. Yeah, and we do that in testing all the time. Good. We're going to have to hold it there. We're out of time. I'm happy to take one-on-one questions after this.